Welcome to Rolls-Royce University Technology Center in Manufacturing and Automotive Technology. My name is Abdul Karik Muhammad. I'm assistant professor at the UTC. Today we are very excited to show you our latest technology in robotics for inspection and repair in a very confined space. Today we are going to show you three different types of robot. The first one is a COBRA robot, which is basically a 5-meter snake-like robot. The second one is a Hexapod robot, which basically it is a walking machine tool. And the third one is a dog robot to do mapping of a working environment. We started developing such kind of robot almost 10 years ago. And the motivation behind that, it is very costly and time-consuming for Rolls-Royce to take an aero-engine from airplane in order to do repair and inspection in situ. And also, it's very challenging to use a conventional industrial robot because of the size limitation of the inspection environment. So we developed such kind of robot, which we call them continuum robot or snake-like robot, to do inspection and repair in a very confined space. As they are very slender, means the ratio between the diameter and the length is very small. We developed different kind and different configuration of these snake-like robots. And today we would like to share with you the latest technology we have developed. It is a COBRA project, which, as I said, it is a 5-meter snake-like robot. Here we have Luca, who is a research fellow at the UTC, who will help us to demonstrate the COBRA robot.
Thank you, Kadik, and thank you all for being with us today. So yes, as Kadik mentioned, that is the COBRA robot developed by one of my colleagues. The system is composed of three main parts. We have the computer, we have the actuation pack, and we have the feed and twist mechanism to insert the robot inside, in this case, inside the paramedical application, inside the mouth of the dummy patient. What I'm going to do now is I'm going to use the joystick to drive the robot inside the mouth, and at the tip of the robot, if you cannot really see, there is a camera with which I can get a visual feedback. That can be very useful, for example, in medical application, to allow the doctor to see what the robot sees moving inside the mouth. Plus, on top of the tip, we also have the camera that will allow us to see better inside the dark space. So I'm going to start moving the robot inside the mouth now. The interesting thing is that apart from the motion that is the feed and twist of the robot, I can also move like an endoscope the tip of the robot. That basically will allow me to see better. So for example, in this case, I'm seeing from the monitor that I'm basically inside the mouth. I pass the tip and I'm looking into the throat. And when I finish my inspection, I can simply retract the robot. And what I was mentioning before is that, as you can see, I can basically drive the tip of the robot to see the determined position. This is clearly very advantageous not only for medical application, but for other application in which I need to drive some camera inside a confined space, for example, an aero-engine. I would say this is everything for COBRA. Thank you, and
thank you very much, Luca. The second robot is a Hexapod Robot, which, as I said, basically is a walking machine tool to do machining in a confined space with very high precision, like 100 micrometers. And the story behind it, we started developing this kind of robot almost also 10 years ago, when Rolls-Royce came to us and asked us to develop a solution in order to do machining of a very large component, which cannot be taken from in situ to a workshop in order to do a machine. For example, drilling a hole of 42 millimeters. We developed for them at the time what we call the pre-Hexapod, which is basically a machine tool with 6 legs. These 6 legs can be moved easily in order to adjust the machine tool to do the machining in situ. After that, we find that the pre-Hexapod still needs the human intervention, so it needs a human operator to take it and install it against the workpiece. So we developed the second version of the Hexapod robot, which is a walking Hexapod, very similar to the free Hexapod, but with walking capabilities. And this is the latest technology we ever developed. It is a rail Hexapod. We developed it in a rail hub, which basically is a EBSRC research hub to develop robotic solution for nuclear environment. And as the main advantage of this rail Hexapod, it is the legs are reconfigurable, so we can change the location of the legs in order to change the speed during the walking, also change the rigidity during the machining. So it can reconfigurable. It can reconfigure. It is set. Josue, if you can help us to give us more information about the rail Hexapod.
Thank you, Khalid. Yeah, as Khalid is mentioning, basically we are bringing machining capabilities to our service environment. And to do so, we have mounted a tool holder. In this case, we have a spindle right now, which allows us to perform operations such as drilling and milling. And we have this tool attached to a platform that basically we control its orientation and its position by modifying the length of 6 limbs that work together. And when the system is in configuration for walking, we control the orientation of each individual limb by these 3 cables and by contracting and extending the limb. And in order to walk in metallic surfaces, we have attached several magnetic feet, which basically work in an off and on position, allowing us to attach and detach from metallic surfaces and also perform machining operations. And this is the brain test, and thank you.
Yeah, as you can see in the videos, the walking Hexapod also has this capability of the walking. It is a little bit slow, but it is basically designed to do the machining as a main task. So the walking is just a capability in order to enable the machining in a very difficult to reach locations. As I said, these two robots, we developed them from scratch in the UTC, including mechanical design, manufacturing, sensors, actuator, everything, including the control as well. But in the UTC also we deal with the off-the-shelf robot. Today, here we have our dog robot, which is off-the-shelf robot. We call it Alex. Alex actually is used in the UTC in order to do mapping of working environment, for example, the manufacturing environment of an aero-engine, where the human operator cannot reach. So just simply by adding a camera on it and using developing some SLAM algorithm, we can map the environment. We have Shonshu, who is now giving the control to Ilyas Ahmed, who left his school in order to help us demonstrating this nice robot. So it is quite easy to be controlled, as you can see. It is simply by a joystick. Yeah, now it's trying to get out of this obstacle. Okay. Oh, oh. So now we are very happy to have any questions from you. Thank you very much for your attention. And if you have any question, please type them in the chat. No question? Yes, thank you for the question. For the snake robot, COBRA robot actually is a 3 years project. We built all of the experience which enable us to quickly develop a new version of it. So, for example, in this project, I mean, it takes yes 3 years to develop the full robot. But if we would like to copy it, I think it will not take us more than 3 months. Yes, the dog robot can run almost similar to the human walking, like 5 to 10 kilometer per hour. Hello? Yeah, please.
Um, that depends. The idea is that we can modify that workspace, but basically it's confined between the legs of the hexapod, and that has a diameter of around 500 millimeters. So we can imagine it as a sphere of 500 millimeters radius.
Yes, this depends, and it does not depend on the robot itself. It depends on the camera and the processor or attached to the robot. So if you have a computer which can take a lot of data, yeah, it can scan as much as you can. Yeah, as I said, it is not related to the robot. Maybe it is related only to the battery size of the robot. is a good question. I think it should be around 70 to 80 degrees centigrade. It is around 5 to 10 kilometer per hour. Yeah, we have previously in an EU project, we combined the snake-like robot with a walking hexapod, the previous version of this one. The snake arm at the time include 24 degree of freedom and 24 degree of freedom also for the walking hexapod. And this to do also inspection of a confined space where you cannot take the snake arm by a human operator. Uh, yeah, actually, we have also some, I think, some robot inspired by flying object, flying animals, in order to develop flying robot. Yeah, we have tried doing the image processing while the robot moving in a normal speed, and we could capture most of the environment features and successfully build a map of the environment. Yeah, the application for for this is machining of a large component in situ, where you cannot take the large component to a workshop in order to do the machining. So imagine you have a very large component in a nuclear site where you cannot send a human to do the operation, and also you cannot take the part itself to a workshop in order to do the machining. So here you have two basic functions. The first one, you need to do the machining in situ, and second one is to send the machine tool over there. So this is a very reasonable application for the Hexapod. The snake robot, yes, it is still operated. We have demonstrated operating it in Derby, while the operator control it remotely from Oxford. In Derby, where Rolls-Royce engine were, and Oxford, where RAS, the other partner of this project, demonstrate to control the snake arm, as I said, from Oxford, using a high-level controller with a joystick. For the Hexapod, currently the controller and the machine are connected with a wire, but yeah, the concept can be easily demonstrated using the remotely control. The dog robot, clearly it is teleoperated with a small distance somehow. Okay, thank you very much for your attention, and I would like to thank all of our team for their collaboration on this event. Thank you very much, guys. Welcome to Rolls-Royce University Technology Center in Manufacturing and in Technology at the University of Nottingham. My name is Abdul Khalik Mohammed. I'm Assistant Professor in Mechatronics at Rolls-Royce CTC. Today we are very excited to show you our latest technology in developing robotics for inspection and maintenance in a confined space. We are going to show you three different types of robots. The first one is a COBRA robot, which is basically 5-meter snake-like robot. The second one is a Hexapod robot, and the third one is a dog robot. We are specialized in designing this kind of robot. We started developing them almost 10 years ago, and the main motivation for that is it is very difficult for Rolls-Royce and time-consuming, also costly, to take an aero engine from the aeroplane in order to do inspection and repair. Also, it is very challenging to use a conventional industrial robot because of the confined space available for the inspection and repair in the aero engine. So that we developed such kind of robot to do inspection and repair in the confined space. Our team today consists of Luca, who are going to show us about the COBRA robot, Josue, showing us about the rain hexapod, Terry and Elias are showing us about the dog robot. So if we started about the COBRA robot, as I said, we started developing this kind of robot almost 10 years ago. We developed different configuration of snake-like robot. And the basic idea of the snake-like robot, they are operated by cables. And basically by manipulating the cable, we can change the configuration of the robot. So COBRA is the most slender robot on the world. It is 5-meter length with 9mm diameter. As you can see here, we have different configurations. This one is 1.5 meter. Here we have a 5-meter version of it. Luca, if you can give us more explanation about the COBRA robot.
Thank you, Khalik, and thank you for joining our virtual booth. So, COBRA robot, like Khalik was mentioning, is composed of three main components. We have the robot itself with the feed and twist mechanism that allows the system to be inserted and extracted automatically from the application that we are analyzing. We have the actuation pack, in which we have the motors for the cable-driven system. And finally, we have the computer that can be used, for example, in this case, to see the visual output from the camera on top of the robot. In this case, in particular, we are showing the application of the robot for medical inspection. The robot can be used for a plethora of applications, going from inspection in confined space to, for example, aerospace engineering, in which we can use it as a borescope. But in this case, we are going to show the application for medical field. In this case, for example, we can use the robot to be driven inside, in this case, the dummy mouth of the patients to see what the doctor will see during the inspection. The camera is also equipped with LEDs, with LEDs that allows us basically to see better in the darkness of the throat of the patient. So now with the joystick, I'm going to drive the robot inside the mouth of the patient. As you can see, I just passed the teeth of the patient, and now I'm going to move towards the throat. Once that I'm in, like I was saying, there is the cable-driven mechanism that allows me to move the position of the robot and basically to see different places inside the target environment. Now I'm going to retract out the robot to show you the potentiality in movement of the robot. The robot just came out, and like I was mentioning, I can now start moving the teeth and control the robot. As you can see, that can be very powerful, not only for aerospace engineering, but also for medical field, allowing a doctor to remotely inspect a patient. Like several other robots that we developed, the system can be controlled not only locally with a connection directly to the system, but also remotely with a level controller. I think that is basically the key points of this application. I will now give the back to Khalik. Thank you.
Thank you very much, Luca. So the second robot is a Hexapod Robot. And we started also developing Hexapod Robot almost 10 years ago when Rolls-Royce came to us and requested for a solution to do machining of a very large component where they cannot take it to the workshop in order to do the machining. So we developed for them a movable or a movable machine tool which can be carried by a human operator with a free 6 legs. So this 6 legs is can be attached to the workpiece, and then the free Hexapod can start doing the machining in situ. After that, we would like to take it further and remove the human from the loop by developing the walking capability of the free Hexapod and convert it into a walking Hexapod. So recently we developed this the latest advance of the Hexapod, which what we call it the rail Hexapod, which is basically a walking machine tool with a reconfigurable legs. So you can see these 6 legs can be reconfigurable in order to increase the stiffness when doing the machining, and also it can change the workspace of the machine tool itself. So, Josue, if you can give us more information about the Hexapod.
Hello everyone, thank you, Khalid. Yeah, basically the system is proving a concept. And the idea is that we can bring machining operations into hazardous environments. And this means that the system has to be able to perform certain operations, meaning drilling, but it also has to be able to displace the reflex of intervention. And to do so, we have a platform which holds a tool. In this case, it's a spindle for drilling and milling. And basically, the idea is that we can control the orientation and the position of the platform by working or simultaneously operating the links by extending them and retracting them. But we can also control individually the position of each limb by moving these 3 tendons. And in order to work on metallic surfaces, we have included some magnetic feet, which basically work on an on-off way in order to attach and detach from metallic surfaces. And when we need to perform, let's say, drilling, we basically keep them on. And this is only during the machining operations, but we will be also showing you some of the videos when the system is working. And in general, this is the explanation of the rain text. Thank you very much.
Yeah.
Thank you very much.
Thank you very much, Josue. Yeah, and the last robot is a dog robot. If you look to these 2 robots, I mean the COBRA and the Hexapod robot, we developed them from scratch. We developed the design, mechanical system, manufacturing, control, sensor, everything. We developed it from scratch at the APC. But also we deal with the off-the-shelf robot. And as an example of that, we have this dog robot here. It is used to do mapping of a working environment, and it is very easy to be used. As you can see here, we have Elias, 6.5 years, can easily control it and manipulate it simply by using the joystick. So what we developed for this robot is attaching some camera on it, and then developing a SLAM algorithm in order to do mapping of the working environment where the human cannot intervene. Carefully. Thank you very much for your attention. If you have any question, please post them on the chat, and we are very happy to answer them. Thank you very much. So here we have Gonzalo asking if we are using the same material to build the robot for nuclear environment and to treat the people. This is a very good question. For the nuclear environment, we know that if you have a robot, you send it to a nuclear environment, it is very likely to have to be affected by the radioactive material. So for that, we propose to include a very thin slab on the body of the robot in order to take any kind of nuclear effect on the robot. This is the first point. The second point, all of our snake arm or snake robots consist of purely mechanical parts, so no electronics attached to the robot, so it will not be affected by the nuclear environment. For the other part, which is a medical application, of course, we consider to use bio-compatible material because it can be very safe for the human operation. Thank you very much, Gonzalo, for your question. Hopefully, I answered your question as well. The Hexapod is around 40 kilograms. Javier here asking how much is the weight of the Hexapod. So it is 40 kilograms. And it can carry up to 70 kilograms of load. Gonzalo asking question, what is the material we are using for the snake, for the cable of the snake robot? Thank you, Gonzalo, for your question. We use steel cables. So Han asking what's the application scenario of the 6-feet robot. So it's basically used to do machining of a large component where you cannot access to this larger component. So you can easily send the the walking Hexapod to the intervention location and start to do machining like cutting, drilling, or threading. So thank you, Javi, for your question. How many years did you need to develop the snake robot? For the COBRA, we spent almost 3 years. It is the length of the project. But yeah, if you would like to copy or develop a similar snake-like robot, probably it will not take us more than 3 months to copy it, because we collected all of the experience needed to build this kind of robot. Maybe I can ask Shunshu to help me to answer this question. Thank you, Kieran, for your question. How long does it take the battery of the robot? The dog robot?
Yeah.
How long does it take?
You mean the life of the battery?
Yeah, of the robot.
Almost every time turning 4 hours.
4 hours.
Up to 4 hours.
Yeah, up to 4 hours. Yeah. Thank you. So, Maratha, thank you for your question. What is the distance that the snake can reach? Yeah, it depends on the length of the snake arm. For COBRA, it is 5 meters, so we can reach 5 meters. And yeah, for this version, it's 1.5 meters, so it can reach 1.5 meters almost. So this is the hexapod while walking. Little bit slow, but guaranteed. Any more question, guys? Please feel free to ask any question. The speed limit, thank you, Martha, for your question. What is the speed limits of the hexapod? The current speed of the hexapod is 10 millimeter per minute, sorry, 100 millimeter per minute, which is quite slow. But as I said, the hexapod is basically developed to do machining with high precision. It can reach up to 100 micrometer of a precision. And the walking is some kind of additional capability in order to enable the machining in situ. Hope I answer your question. Thank you very much, guys, for your attention. And I would like to thank all of our team for the collaboration on this show. Thank you very much, guys. Welcome to Rolls-Royce University Technology Center in Manufacturing and Engineering Technology at the University of Nottingham. My name is Abdul Khalid Muhammad. I'm Assistant Professor in Mechatronics at the UTC. Today we would like to show you our latest technology in developing robotics for in-situ inspection and repair. Today we are going to show you 3 different types of robots. The first one is a COBRA robot, which is basically a 5-meter snake-like robot. The second one is a Hexapod robot, and the third one is a dog robot. So we started developing such kind of robot almost 10 years ago, and the motivation behind that it is for Rolls-Royce it's very costly and time-consuming to take off an aero engine from the aeroplane in order to do inspection and repair. As the inspection and repair inside aero engine is very challenging because the available working space is very limited. So it is we cannot use conventional industrial robots. So we developed this kind of robots, which is we call them snake-like robot or continuum robot. Here we have our team today will help us to do demonstration. We have Luca working on the COBRA robot. We have Josue working on the Hexapod robot. We have Candy and Elias who will help us to demonstrate the dog robot. So if we start with the COBRA robot, Luca, if you can give us more information about the COBRA robot.
Thank you, Tariq, and thank you all for joining Target Robot. So yes, like Tariq was mentioning, this is COBRA robot is one of our newest snake-like robot. The system is composed of 3 main elements. We have the feed and twist mechanism that basically drives the snake robot inside the application. We have the actuation part that contains all the electronics and the motors to drive the cable-driven system inside the robot. And finally, we have the computer, in which, in this case, for example, we can see the output of the camera on the tip of the robot. The robot can be used for a plethora of applications, going from inspection in constrained spaces, going to aerospace, up to medical field. In this case, since it is for a medical application, for inspection inside, for example, like an endoscope, we just have a camera with some LEDs that basically shine light through the darkness of the throat of the patients. But we can put on the tip of the robot also others, any kind of tool, going to lasers or to other kind of milling bits. I'm going to show you now the system. Here we have the joystick with which I'm going to drive first the robot inside the mouth of the dummy patient. I'm passing now through the teeth and entering in the direction of the throat. Then I can use the cable-driven mechanism to rotate the robot and have a better view of the inside of the mouth of the patients. Now I'm going to retract the robot, so I'm going to show you more clearly the capability of steering the teeth through the cable-driven mechanism. And as you can see, I can remotely operate the robot. The big advantage of this system is that it's not only remote, meaning from here to here, but can also be remotely from different locations through wireless connections. And as you can see, that can be very useful, for example, for inspection in aero-engines or for medical application where I have a limited number of very qualified doctors or engineers doing inspection remotely and not having to be deployed directly where the application is.
So, Luca, have you demonstrated like a remote operation of this kind of robot?
Yes, we did it from Derby to Sheffield, and basically we succeeded in this. That is not the first time we did this. We also did it for other projects, for example, in Rainer. And like I was saying, the key factor is to have a limited number of very qualified engineers or doctors that don't need to be deployed all around the world.
And how long does it take you to develop this robot?
The development of this one was around 3 years. Let's say that is roughly the standard for all robots. Of course, since we are kind of expert in this, and I would say in the world of snake-like robot, we are some of the most qualified group in the world. The development time is getting shorter and shorter, but I would say 2 years is what you should expect for a full robot to be deployed.
Thank you
Thank
very
you.
much.
Thank you.
Yeah. So the second type of robot is Hexapod Robot, as you can see here. And we started developing this kind of robot also almost 10 years ago, where Rolls-Royce came to us and asked for a solution to do machining of a very large component where the component cannot be taken from where it is located to a workshop in order to do, for example, drilling of M42. So we developed for them at the time what we call the free Hexapod, which is basically a machine tool which can be carried by a human operator and attach it against the workpiece and then start to work, make the drilling or the machining in general. After that, we found that it depends on the human operator, so we would like to take the human from the loop by developing what we call a walking Hexapod. So basically, it is a walking machine tool which can walk into the intervention location and start doing the machine. And this is the latest technology we have developed for the Hexapod robot, which what we call it the rail Hexapod. And Josue, if you can give us more information about the rail Hexapod and how it's different from the previous variant of the Hexapods.
Thank you, Khalid. Well, basically, the idea of this Hexapod is that we are enabling other capabilities. And as Khalid was mentioning, the idea behind it is to make a system which is able to adapt to different environments. And for that, we included a clutch mechanism, which basically can modify the structure of the system and allow other capabilities, such as increasing the workspace and increasing the stiffness. And the idea behind that is that we are bringing machining capabilities to hazardous environments. And to do so, we have a tool that we have attached to a platform. And the position and the orientation of this tool is controlled by modifying the orientation of the platform. To do so, we have 6 links working together. And by means of extending them and retracting them, we can move people of the tool to do, for instance, drilling operations or milling operations. And we also will be showing some videos of the system working. But basically, the idea is that we can control the orientation of each link individually by modifying these three cables, and by contracting and extending each link individually. And in order to work on metallic surfaces, we have also included these magnetic feet, which work in a passive active way, basically on and off, as we are displacing over, let's say, different environments. And when we are doing the machining, we keep them on in order to attach it to the surface. And in general words, this is the description of the rain text. Thank you very much.
Thank you very much, sir. We would like also to mention that this rail Hexapod is developed under EBSRC Research Hub, which is rail, robotic, and artificial intelligence in nuclear. And it is developed to do this machining task in a nuclear environment. Also, would like to make note about the COBRA robot, which is developed in innovative care project led by Rolls-Royce. These 2 projects, we developed them from scratch, as most of our robotic system, including the mechanical design, manufacturing, sensors, actuators, and control system. Also, we deal with off-the-shelf robot. So here we would like to share with you our Alex robot, which is basically a dog robot. Alex is sleeping now. I think it's coming. Yes, quite shy. Yeah. So Alex is a dog robot. We developed a SLAM algorithm for it in order to do. Okay, and as you can see, the interface of the robot is quite easy. It has 6.5 years. It can easily operated through a joystick. So it can move forward, back, it can rotate, and it can flip upside down. Okay, be careful, be careful. Back now, back. Now. Yes, very good, very good. Yeah. Okay, thank you very much for your attention. Now, if you have any question, please post them on the chat, and we are very happy to answer them. Yeah, thank you very much, Gonzalo, for your question. For the COBRA robot, it is already reached TRL 6, and we are now working on commercializing it with Rolls-Royce. Yeah. We receive a lot of interest in this particular robot. Josue, you can help me answering this question. How strong is the magnetic field of the Hexapod? Thank you, Kiran, for your question.
Thank you, Kiran, for your question. We have tested and we have been able to withstand 50 kilograms against the feet.
Hmm. Thank you very much, Gonzalo. So Gonzalo asking if we are using the same material to build the robot for nuclear environment and for the treatment of the human people. So for the nuclear environment, it is very likely that the robot can be wasted by the nuclear waste. So basically, we propose to use a small slave on the robot. So even if the slave is contaminated with the nuclear material, so we can take it out from the robot easily. And for the human or the medical operation, we are planning to use bio-compatible material in order to enable safe operation inside the human body. Thank you very much, Gonzalo, for your question. Yeah, for COBRA, for example, we operated COBRA in Derby, where the Rolls-Royce aero-engine is located, and we controlled it remotely from Oxford, where other partner developing, who participate in developing COBRA, make the high-level control. So they controlled it through a joystick from Oxford. So it is almost very large distance. For the robot, yeah, it can. For the dog robot, it can be teleoperated, but on a small distance. And for the Hexapod, currently it is wired control. Thank you, Abby, for your question. So, what other animals do you think that could inspire more robots? Actually, almost most of the animal can inspire us to design robots. But recently, we have a particular interest in flying objects or flying birds in order to develop, inspire us to develop one new robot. I think soon we are going to announce about it. Oh. Yeah, do you have any other question, guys? Feel free to answer to ask the question. Thank you, Martha, for this question. Are you planning to implement artificial intelligence? Yeah, we already started to implement a lot of artificial intelligence, like neural networks here in our robots. For example, for the snake-like robot, it is very difficult to do like the control of the position due to the limitation of the sensors. So we have some PhD students working on developing neural networks and artificial intelligence in order to improve the closed loop control of it. Thank you for this question. Yeah. For myself, I'm more like the cats more than the robot, as the dogs. Yeah, and I hope at some point we can do a cat robot. Feel free to ask question, guys. We are here to answer your question. And if you have any other question, I mean, after this live, you can post them to our email addresses, or you can visit our website. Also, after fully releasing the COVID-19 restriction, if you are interested to visit our lab, you are welcome. Just let us know. This is a walking hexapod while doing the walking task. You can see it is quite slow, but yeah, as I said, the main purpose of this walking hexapod is machining capability. So it can do very precise machining with 100 microns. Thank you very much for your attention, guys. And I would like to thank all of our team members for their collaboration on this live. Thank you. Welcome to Rolls-Royce University Technology Center in Manufacturing and Automotive Technology at the University of Nottingham. My name is Dr. Tariq Mohammed. I'm Assistant Professor in Mechatronics at the ATC. And today we would like to share with you our latest technology for robotics for inspection and maintenance in a confined space. Today we are going to show you three different types of robots. The first one is a COBRA robot, which is basically 5-meter snake-like robot. The second one is a Hexapod robot, and the third one is a dog robot. So we started developing such kind of robots almost 10 years ago, and the motivation behind that is that it is very costly and time-consuming for Rolls-Royce to take off an aero engine from the aeroplane in order to do inspection and repair. Also, the available inspection and repair environment inside the aero engine is very small, so we cannot use a conventional industrial robot because their size limitation and ability to manipulate inside an aero engine. So we developed this kind of robot. Today we have our team here helping us to demonstrate the different type of robot. We have Luca working on the COBRA robot. Yeah, we have Josue working on the rail Hexapod, and we have Tianji and Elias showing us the dog robot. So if we started with the COBRA robot, as I said, we started developing this kind of snake-like robot almost 10 years ago. We developed different kind of configuration, almost 10 different configuration of snake-like robot with different lenses and different purposes. This is the latest technology. It is 5-meter snake-like robot, and it is almost the most slender robot in the world, with 5-meter length and 9mm diameter. Luca, if you can give us more information about COBRA and its capabilities.
Yes, thank you, Tariq, and thank you all for joining our robot. Like Tariq was mentioning, we have several configurations of the robot. We have the 5-meter version of the snake probe and the 1.5-meter version of the probe. The system is composed of three main parts. We have the twist and feed mechanism that is used to insert and rotate the probe inside the application. We have the actuation part that contains all the electronics and the motors for the cable-driven mechanism. And finally, we have the computer that we can use, for example, in this case, to get the visual feedback from the camera. The system, we not only have a different length, but we also have a different end effector to do different kind of tasks. In this case, we are going to show you how to do inspection inside a dummy patient for medical application, but the robot has also been used for inspection and repair in aero-engines or in confined spaces. I'm going to now move the probe inside the dummy patient. So now the probe is entering into the mouth. I can now start moving the tips, and that will allow me basically, and this will allow me to see better inside the mouth. And now I'm going to retract the robot.
So Luca, what is the working principle of snake-like robot in general?
Yes, so basically in snake-like robot we have some actuator. In particular here we have some rotary actuator that pulls literally cables. That is why they're called cable-driven. And when I pull the cable, it's like thinking to like some kind of toy with pulling strings. The tip is going to bend in different directions. The big advantage of this system of actuating robot is that I can have all the actuation part outside the probe, and that allows me to have a very slender end effector. That can be useful, for example, in inspection, for example, either in aerospace, where I have the blades of the engine that doesn't allow me to go on with very bulky system, or for example, in medical field, where obviously I want the probe to be as small as possible in order not to damage and to cause discomfort to the patient.
And why do you need this feed mechanism?
Yes, that is actually a very good point. So let's go back to the in particular to to the boroscope for aerospace engineering. Usually, there is an actual operator that has to feed manually the boroscope inside the engine. This is clearly not optimal because it's better to it's not very accurate since the operator doesn't have the visual feedback of what is happening, and actually the tactile one. In this case, we can basically um, combine everything inside our calculation part in which we have a sensor that can provide a uh, much better accuracy to the moment. And on top of this, there is also the aspect of teleoperation. If I want, for example, to have the operator to move manually the end effector, that is, of course, doable if the operator is on place. But if we think, for example, to very specialized tasks in which there are very limited number of very skilled operators, either engineers or doctors, to do certain tasks, is definitely optimal to have something that can be controlled remotely. And in this case, I can simply deploy the system and have the operator thousands of kilometers away, and they can still do the operation like it was in the place.
Yeah. Thank you very much, Luke.
Thank you.
Yeah. And the second robot is Hexapod Robot, as you can see here. And yes, the history also of the Hexapod Robot was almost similar to the snake-like robot. We started it almost 10 years ago when Rolls-Royce came to us and asked for a solution in order to do a machining of a very large component which cannot be taken from the, from its location to a workshop in order to do a machining. So we developed for them a free Hexapod, which is basically a small machine tool with free 6 legs, can be attached against the workpiece in order to do the machining. We found also the free Hexapod still needs a human intervention. So we developed what we call the walking Hexapod, which is basically a walking machine tool, can walk to the location of the intervention and start doing machining after doing calibration automatically using image processing. And recently we have developed this RAS Hexapod, which is a walking machine tool with reconfigurable legs. So Josue, if you can give us more information about the RAS Hexapod and what is its advantage compared to the previous version of the Hexapod.
Thank you, Kelly. Yes, as Kelly was mentioning, the idea behind this Hexapod is to enable further capabilities. This means that we have an adaptive system which can modify, for instance, its stiffness and the workspace where it can work. Basically, those are the positions where the end effector can be positioned. And to do so, we have mounted a tool connected to a platform. And this platform basically is controlled by 6 links that work together by extending them and contracting them to modify the position and orientation of the tool. For instance, if we want to do drilling or milling operations, and for instance, when we are walking, what we do is that we control the position of each limb individually by modifying the position of these tendons in terms of their length, and also by controlling the length of each limb. And also, to walk on metallic surfaces, we have included this magnetic feet, which can attach and disattach to magnetic surfaces. And for instance, when we are doing like machining operations, basically what we do is we keep them on to keep the system attached firmly to the surface. And then we can, for instance, modify the position of the upper joints to enhance the machining abilities. And also we can modify the position of these upper joints for working in different configurations. And in general words, this is the description of the system.
So what's the control system you use to control this Hexapod?
Well, we have the communication between several systems. For instance, we have drivers that control directly the motors. This is they send required voltage and current. And we have 2 FPGAs, which send the signals to the drivers. And these FPGAs are controlled by the kinematics, which are in this computer. So we have 3 layers of controllers.
And how long does it take you to develop this Hexapod?
I think it has taken us around 2 and something years, how we could say. mainly because we have to develop things and we test them.
So which project you developed this one?
This is for a project, a bigger project called RAIN, which basically integrates robotics and artificial intelligence for nuclear applications.
Thank you very much for that.
Thank you.
Yeah, for these two robots, we developed them from scratch. So we started by the concept, the mechanical designs, actuation, sensors, controller, everything we designed it from scratch. And at the UTC also we work always off-the-shelf robot. The third robot today is our off-the-shelf robot. It is a dog robot. We call it Alex. So Alex can be easily controlled by a joystick, and we develop a SLAM algorithm based on image processing in order to do mapping of a working environment. So here, as you can see, we have Elias, who is 6.5 years, who easily can control it by using the joystick, showing the capability of the robot. Of course. Yeah. So thank you very much for your attention. And if you have any questions, please post them on the chat, and we are very happy to answer them. Yeah. Thank you very much, Zan, for your question. So your question basically about the accuracy of the snake-like robot and how we can make sure that they are at the correct position. So for the COBRA robot, we have a fiber optic sensor, and this fiber optic sensor can be attached inside a working channel inside the robot. So here inside the robot, we have a free working channel, so we can send any kind of sensor or tools. So we insert a shape sensor, which can basically give us indication about where each point of the robot is located with a very high accuracy. So based on this, we can implement a feedback controller in order to adjust the robot to the required location. Okay, thank you, Martha, for your question, which is which are the improvement or next steps for your 3 robots? Okay, basically for the COBRA robot, one of the improvement we are doing right now is that the passive bar, if you insert it, for example, in a large space, so it is very difficult to adjust the robot in a large space, if you can imagine, because the robot itself is, the passive part is not controllable. So what we are developing right now is to have an inflatable balloon, which can be attached to any location of the robot. So this inflatable balloon can rigidize the robot against the environment, so it can be more controllable. For the Hexapod, I say, so can you help me answering this question?
Yes, sir. For instance, one thing we have foreseen is that we need to develop systems which are highly adaptable to different systems. And basically, some of the things that we have learned from our experience is that one of the things that we have to keep constantly in mind is make systems which are easily transported to the place of intervention. So basically, we are targeting to create adaptable systems and live systems.
Yeah, okay.
Thank you.
Yeah, for the dog robot, actually, there are a lot of, I think, environment where we can improve. If we look to the low-level control system of it, so its dynamic system can be improved as well. Think somehow also the battery life and this kind of stuff in order to allow it to survive for longer time. Yeah, the accuracy also of the SLAM algorithm we developed needs some improvement. So this is actually the most active area we are working on. So it's the accuracy of the SLAM algorithm we developed. The current, thank you, Karen, for your question, which is a snake robot is waterproof? The current version of the robot, it is not. But another important point that all of the component of the snake-like robot, I mean the robot body, is a mechanical parts. So it is by default, it can be regarded as a waterproof, but it needs a little bit improvement in order to be fully waterproof against corrosion and some this kind of things. But as I said, the mechanical parts, the body part of the snake arm is just purely mechanical parts, no any kind of electronics inside it. Any other question, guys? We are happy to answer. So this is the hexapod while walking. As you can see, it also can walk on an inclined surface. Thank you, David. David Alatori, who is work mainly on developing this COBRA snake arm. Thank you very much, David, for your hard work on this robot. Without it, this robot could not be here. Okay. Thank you very much, guys, for your attendance and watching us. Thank you also for your question, which inspire us for further development of our robots. I would like to thank our team, all of them, for their hard work. I'd like to thank Luca, Josue, Shunshu, Elias, and Tianji who participated in the demo. And I would like to thank all of the guys behind the camera, Ehwa, Rati, Cecilia, Weming, and Matteo. Also, if you'd like to see more about us, you can visit our website. You can also see our YouTube channel, which we posted already on the chat. And finally, I would like to thank two of our college, Professor Dragos, who is the director of Rolls-Royce UTC, and Dr. Erwin Dong, who is the first person maybe started working on the snake-like robot in his PhD until now. And I would like to thank all of the members of the UTC who participate in developing this kind of robots. Thank you all.